So, this is the last lecture of this course. We will finish with a general introduction to multiplicity theory. Multiplicity theory itself is an interesting topic, but we will not be going deep into it. If you go back to the spectral measure version of the spectral theorem, whether it is self adjoint or the normal operator case, we are identifying our normal operator. So, let us take the case of the single normal operator as a multiplication operator on some L2 space. Now, the way we did this was we start with the cyclic case, that means there is a vector which is a cyclic vector, and via representation theorem we got a measure and we identified our operator as multiplication by x or multiplication by z on the measure space, right, on the L2 space. Now, if it is not the cyclic case, in the general case we start with one vector, look at the cyclic subspace generated by that, go to the orthogonal complement, pick up another vector and continue. So, the measures you got were dependent on the way you chose those vectors and generated the cyclic subspace. So, the uniqueness was missing there. So, multiplicity theory essentially addresses this question. We will see that if you do this in a somewhat ordered way, not arbitrary, of course, that has to be made precise, then there is uniqueness in the sense that the measures that appear will have to be mutually absolutely continuous with respect to each other. Okay. So, let us look at the simple case first. Simple case would mean the cyclic case, and then I will write down the general theorem. We will not be proving the theorem. Okay. So, multiplicity theory. Multiplicity theory. So, this is similar to the finite dimensional case, where if you have two normal matrices, they are equivalent, if unitarily equivalent, if and only if the eigenvalues are same and the multiplicity of the eigenvalues. The multiplicity here would mean the dimension of the eigenspace corresponding to that eigenvalue, they are same, right. So, that is a unitary invariant. So, these two quantities essentially determine the operator. Any other operator with the same data will have to be unitarily equivalent to this operator. In the infinite dimensional case, the eigenvalues do not exist. So, dimension of the eigenspace may not make sense, but the multiplicity still has some meaning. Okay. So, that is what multiplicity theory deals with. We will, as I said, look at the cyclic case, the simple case first. Okay. So, we will as usual look at the self adjoint case first and then see how it is for the normal operator. Both the proofs are actually here essentially the same. Okay, so, let mu be a positive measure on a compact set in R. Okay, so, it has bounded support, okay, compact set in R. Let mu, so I am going to define a operator mu. What is mu? Mu is the measure. Okay. So, m simply stands for multiplication by x, because now we are doing things in the real line. So, that means self adjoint case, spectrum is contained in the real line. Mu from L2 of R d mu to itself, okay, L2 of R d mu. Okay. So, remember mu is a positive measure, positive you can assume finite, I did not write that, finite positive measure on a compact set. Okay. So, think of -1 1 or something like that with Lebesgue measure, it does not matter. The multiplication operator m sub mu is defined to be m sub mu f. So, I should tell you what it is at a point x. So, that is simply x f of x. Okay. So, mu has bounded support. So, it is the x runs over only on the support of mu, right. So, you can take the supremum of x over the support of mu outside and you will get a bounded operator, right, and it is clearly self adjoint. Okay. So, mu is bounded self adjoint operator. Right. Now, what is important in this case is, this is the cyclic case in the sense that the constant function 1 is a cyclic vector. Note that the constant function 1 so let us denote it by 1 is a cyclic vector, is a cyclic vector for mu, right, because if I look at 1 and I apply mu, well, why is that? So, mu to the L, it is self adjoint. So, there is no star, you have to take the adjoint as itself acting on 1, right, that is supposed to be a function. So, that is simply x to the L, right. So, if I look at the span of all this m sub mu to the L acting on 1 and take the span of that, I will get all polynomials. Now, remember mu has bounded support, right. So, you are inside a compact set. So, if I get all polynomials in x and the compact set is inside the real line, I have all continuous functions by taking uniform limit, right, but it will converge in L2 as well, right, mu is a finite measure and all that. So, I will get all continuous functions when I take the span closure with respect to the L2 norm, and continuous functions are dense, and so m mu L acting on 1, if I take the span of that, it is going to be all of L2, right. So, since span m mu L acting on 1, L equal to 0, 1, 2 etc. is dense in L2, right. So, it is a cyclic vector, and the spectral theorem says that if I have a self adjoint operator A which has a cyclic vector, then the cyclic vector V can be mapped to constant function 1, and I can write A as multiplication by x, right. So, the spectral theorem says that any self adjoint operator, right. So, any self adjoint operator A with a cyclic vector is unitarily equivalent to m sub mu for some mu, right, is unitarily equivalent to m sub mu for some mu, right. For some mu, right, on the real line, because it is self adjoint and so on. So, such operators are called simple operators, but we will not bother about the definition. It has a cyclic vector. So, it will be identified as m sub mu for some mu. Now, let us see when. So, essentially I want to know when two self adjoint operators with cyclic vectors are unitarily equivalent. That question is same as if I take two operators m sub mu and m sub nu. So, those are the model operators for self adjoint operators with a cyclic vector, right, they will look like that. Question is when are they equivalent? What can you say about the measures m sub mu, the measures mu and nu if the multiplication operator m sub mu and m sub nu are unitarily equivalent. Okay. So, that is the theorem. Okay. So, let us see theorem. So, how much those measures can change. Okay. So, let mu and nu be two positive finite measures with compact support, okay, compact support in R, because we are doing the self adjoint case first, and we will see essentially the same proof works for the normal operator case as well. And mu and nu be two finite measures with compact support in R, then then m sub mu. So, m sub mu is the multiplication by x on L2 of mu, right, on the real line, then m sub mu and m sub nu. So, we have two multiplication operators. Also, as I said, the spectral theorem says that if you have self adjoint operator, bounded self adjoint operator with a cyclic vector, it has to look like m sub mu, right. So, we are, the theorem is that if I have A and B, two self adjoint operators with cyclic vectors, then they are unitarily equivalent if the corresponding m sub mu and m sub nu are unitarily equivalent, if and only if the measures are absolutely mutually absolutely continuous. Okay. So, then m sub mu and m sub nu are unitarily equivalent if and only if, okay, mu is absolutely continuous with respect to nu and the other measure nu is absolutely continuous with respect to mu. Okay. So, let us prove this. Proof is simple, but before that look at m sub mu and m sub nu. They are multiplication by x, right. Both operators are multiplication by x, only thing is they are on different measure spaces, right. The measures are mu and nu. But if you have a multiplication operator, the spectrum of the multiplication operator is the essential range of the function you are multiplying with. What are you multiplying with here? You are multiplying with the function x, right, x going to x on the support of mu, similarly on the support of nu. So, if m sub mu and m sub nu are unitarily equivalent, their spectrums are same. So, spectrum of m mu and spectrum of m nu both are compact subsets of the real line and they are same. But what is the spectrum of m sub mu? Well, it is the essential range of the function x going to x with respect to the measure mu, but that is simply the support of mu, right. And similarly, for m sub nu, the support of nu is the spectrum, but if they are unitarily equivalent, the supports will be same. So, both mu and nu are supported on the same set, right. So, then now you see that the absolutely continuous part makes complete sense, right. The mu is absolutely continuous with respect to nu and nu is absolutely continuous with respect to mu. Okay. So, you can see that this has to happen in some sense. So, let us prove that. Okay. So, let V be the unitary, right. So, I have V from L to mu to L to nu, okay, L to nu unitary. Okay. So, it is a unitary operator between these two L2 spaces which intertwines these multiplication operator, right, such that V inverse. So, V inverse will take L2 of the right hand side nu to L2 of mu, then you apply the multiplication operator here, then you go back via the unitary V, you should get the other operator, right, m sub nu. Okay. That is, so to write it bit more clearly, that is, you can take the V inverse to the other side. So, I have V m sub mu equal to m sub nu times V, right. V intertwines these two multiplication operators. Okay. Then, so I can take powers of m sub mu and m sub nu and the same intertwining property will happen, right. So, then V m sub mu to the L equal to m sub nu to the L V for every L, right, L equal to 0, 1, 2 and so on, right. Okay. Now, remember that the constant function 1 is a cyclic vector for m sub mu. So, let us apply that. Okay. So, apply these operators on the constant function 1. Okay. So, constant function 1. Okay. So, we will denote it by 1. So, we will get V acting on m sub mu to the L acting on 1, right. So, V times m sub mu to the L acting on the constant function 1 equal to m nu L V 1, right. So, remember V is a unitary from L 2 of mu to L 2 of nu. Okay. So, the constant function 1 is here, right. So, that will be pushed to some function on the other side, right. So, V 1 is some function, let us call that g. Okay. So, if V 1 is g, if V of the constant function 1 is a function g, well, where is g? G will have to be in L 2 of nu, right, on the other hand side, because V is the unitary map which takes L 2 of mu to L 2 of nu. What do we get from here? So, we get on the left hand side we have V acting on, well, so we will get V acting on x to the L, right, mu L acting on 1, that is simply x to the L, right. So, when I say V acting on x to the L, I am looking at x to the L as a function on L 2 of mu, the left hand side, and V will take it to the right hand side, right. So, V is acting on this equal to, on the right hand side V 1 is my function g, right, this is g, and m nu to the L is simply multiplication by x to the L, right. So, that is x to the L times g of x. Okay. So, the notation is slightly not correct, I should put V x to the L, it is a function evaluated at x equal to this, okay, but I am sure you understand this. So, that is how V acting on x to the L looks like, right. That is trivial, right, because 1 goes to g. So, x is x times 1, that has goes to x times g, and x square has to go to x square times g and so on, right. Okay. So, now we have to use the fact that V is unitary. So, our aim is to prove that the measures are mutually absolutely continuous. We will prove one way, one measure is absolutely continuous with respect to the other measure, and use V inverse to get the same answer, right. So, it is enough to prove one of them. So, now if I look at integral over x to the L mod g of x square d nu. Okay. So, nu is the measure on the right hand side. So, let us look at this quantity. Well, what is this? This is, you look at x to the L. So, let me write one more step, g of x bar d nu, right. So, now this looks like an inner product, right, inner product of x to the L g of x times g, right, with g. Well, what is that? So, this is nothing but x to the L g x is here, right. So, I have, well, let us write x to the L g of x, the function, and inner product with the g of x in L 2 of nu. Okay. So, generally one does not write x there, because it is x to the L, I wanted to put that, right. The function x to the L g of x, inner product with the function g, right, that is what we have. Okay, which is also equal to, now we use the fact that x to the L g of x is given by V of x to the L. So, I have V of x to the L, that means the unitary operator V acting on x to the L, which is a function in L 2 of the second measure nu, right, and the g is just V acting on 1, right, we know that, but we are still in L 2 of the function L 2 of the second measure nu. But now it is V acting on some function, inner product with V acting on another function, but V is unitary. So, it preserves the inner product. So, this is simply x to the L inner product with the constant function 1, but now V is gone, and so you are back to L 2 of mu, okay, which is equal to integral x to the L d mu x, right, the constant function 1 will give me just, okay. So, where did we start from? We started from here, we ended up here, right. So, let us rewrite that, that is integral over x to the L mod g of x square d nu x equal to integral over x to the L d mu x for every L equal to 0, 1, 2 etc. right. For all L this will work. Okay. Okay. So, this implies well. So, now this is a standard argument. So, if you have already we have already seen this in fact in this course itself. If I look at this measure mod g x square, that is a positive function, times nu, right, that is my measure. That measure and the measure mu will have to be the same, because they have the same moments, right. So, if you want an argument, you look at linear span of x to the L, those are polynomials. Since they agree on x to the L's, you can integrate against any polynomial, you will get the same answer. Then you can take the limit, uniform limit, you will get all continuous functions instead of x to the L, but then measures are in the dual of continuous functions, and so they will have to be equal. Okay. So, hence, so this is something which you can complete, hence it follows that mod g f x square d nu x equal to d mu x, right, or in other words this simply says that nu is absolutely continuous with respect to mu, right. But then nu and mu are arbitrary, like we can change the order and then we will see that they are same, right. So, bisymmetry or use V inverse if you like, you will get the other way, right. So, by symmetry we get mu is also absolutely continuous with respect to nu. So, now you see that if I have these multiplication operators on compact sets with respect to certain measures, they are equal, and so this is what this is the starting of the multiplicity scene. They have they are unitarily equivalent if and only if the measures are absolutely continuous with respect to each other. You can apply this to finite dimensional case and see what happens, because the measures are going to be point masses, right, at the eigen values. So, absolutely continuous will mean they are essentially the same. So, you will see what this theorem says for the finite dimensional case, that is an it will illustrate what is going on. So, let me write down the definition. So, we will prove the same result for normal operators and then state a major theorem which tells you about the uniqueness of the measure class. Okay. So, definition: two measures are equivalent if they are mutually absolutely continuous with respect to each other. So, mutually absolutely continuous with respect to each other. Okay. So, whatever we just saw, mu is absolutely continuous with respect to nu, and nu is absolutely continuous with respect to mu, right. So, then we say mu is equivalent to nu, and that is clearly an equivalence relation, and the equivalence class is called the measure class. Okay. So, an equivalence class is called a measure class. Right. So, if I say measure class of a measure mu, that means you put all those measures which are mutually absolutely continuous with respect to mu, right. So, mu and nu are mutually absolutely continuous with respect to each other if mu is absolutely continuous with respect to nu, and the other way is also true. Put together all of them together, you get the measure class of mu. So, what we have seen just now is in the unitary equivalence of multiplication operators, it is possible to change the measure, right. But you can't do this in an arbitrary manner, you will get something which is mutually absolutely continuous with respect to the measure you started with. Okay. So, what we proved was one way, the other way is actually trivial, I will leave it as an exercise to you. What we proved was if m sub mu and m sub nu are unitarily equivalent, then mu and nu are equivalent. Other way is trivial, if mu and nu are equivalent, then there is a Radon-Nikodym derivative and there is a unitary which you can write down explicitly, right. Look at how we helped us in getting the Radon-Nikodym derivative in the proof, okay. It is essentially the same. Okay. So, the result for normal operators is essentially the same. So, now except that the spectrum now is a subset of the complex plane. So, we have to go to the complex plane instead of sticking to the real line, but the proof is essentially the same. Now, let mu be a finite measure, finite positive measure supported on a compact set in the complex plane. Okay. So, on a compact set in C, right. So, okay, maybe let us give it a name, so that we use sigma, right, a compact set sigma contained in C. Okay. So, mu now is going to be multiplication by Z. So, mu is from L2 of sigma mu to L2 of sigma mu, or you can look at the complex plane, mu is supported on sigma anyway. Mu f of Z is equal to Z times f of Z, right. F is in L2 and Z is in sigma, right. So, that is because sigma is compact, this is a bounded operator, it is a normal operator and it does the constant function 1 is again a cyclic vector. Okay. So, check that constant function 1 is a cyclic vector. Okay. So, now remember you have normal operator. So, you also have to apply the adjoint. Okay. So, multiplication by Z star. So, you will get all powers of Z, all powers of Z star, all mixed powers. So, you get all polynomials and the same argument works. Okay. So, theorem is whatever we did earlier for self adjoint operators. Let mu and nu be two positive finite measures with compact support, okay, with compact support in the complex plane now. Okay. Then mu is equivalent to mu. So, that is unitarily equivalent, these two operators are unitarily equivalent if and only if the measures are equivalent, right. That means, mu is absolutely continuous with respect to nu and vice versa. Well, so we will quickly prove this. Proof is the same. So, we have a unitary from L2 of mu to L2 of nu, right, and as such that V m mu V inverse equal to m nu, right. As earlier let V 1 equal to g, right, the one constant function 1 goes to the function g on the other side. Now, consider, so the only difference is here. So, now consider, earlier we simply looked at x to the L, but x to the L gives me all polynomials in one variable. That is not enough when you go to the complex plane, because you have x and y, right. So, you need two you need polynomials in x and y or polynomials in z and z bar. Okay. So, now consider integral z to the L z bar to the k mod g z square d nu, okay. Right, that is the only difference in the proof. So, this is equal to, let us write this as z to the L g z times z to the k g z and then take the bar, right. So, that is the inner product. So, this is nothing but the inner product of, well, what is this? This is m nu L V 1, right. V 1 is g and m nu L will give me z to the L. So, that is the first term. The other term is m nu k V 1 again, right, in L 2 of nu, right. So, you will get z to the k g z and then you take the complex conjugate for the inner product. But then this is because V intertwines these two operators, I will have V acting on m u L of the constant function 1 and V acting on m V acting on m mu to the k on the constant function 1, but again the inner product is still here. Now, V is unitary, so V disappears as in the earlier proof, but I have m u to the L constant function 1, m u to the k constant function 1 inner product with L2 of nu, right, which is nothing but integral. Now, I have z to the L and z to the k bar, right. So, that is z bar. So, z to the L, z bar to the k d mu, right. So, here the measure is mu. Okay. So, I started with this and I ended up here. So, z to the L, z bar to the k, if you take the span of that, I will get all polynomials. So, the measure here and the measure will have to be same, right. So, this implies mod g z square d nu is equal to d mu and vice versa, right. So, this is the same thing, all right. So, this takes care of only the simple case, that means there is a cyclic vector. So, I will write down the major theorem and then stop. I will not get into the proof of that theorem. Okay. So, theorem let A, so we will write it down for the self adjoint case. Okay. So, let A be a bounded self adjoint operator. Okay. Then there exist measures nu j equal to 1 to infinity, it can be finite also, but infinity supported on minus norm A to norm A, because we are looking at the self adjoint case. So, the measures are all supported there such that nu 1 is, so well, I should write oh, I did not define this part. Well, okay, I will just give the reference. Okay. So, and A is unitarily equivalent to direct sum L equal to 1 to infinity nu L on the direct sum of L2 of minus norm A with respect to these measures, okay, j equal to 1 to infinity. So, if I choose these the measures appropriately, then I have this equivalence, and the measure class of, moreover the measure class of nu j are unique. Okay. So, that is what we have seen earlier, right. So, that is the theorem. So, let me give you a reference for this, I am not going to prove this. So, reference the book by Barry Simon, operator theory. So, it is titled operator theory. So, most of this second half of the course material is taken from this book. So, this is a part 4 of 5 books which Barry Simon has written recently. So, a comprehensive course in analysis part 4. Okay. So, that is the end of the course. We will stop here. We have proved the spectral theorem in various forms now. So, we started with the single operator case. We proved that the projection valued measure or the resolution of identity case, and also as multiplication operator on appropriate L2 spaces. And then we without using the C star algebra technique, we did this again using the resolution of identity and developed spectral theorem for Selford joint operators, and we ended with commuting family of Selford joint operators. Okay, so we will stop here.